So start out with just a simple Fisher projection. You guys will do a aldohexose. And we're going to practice going back and forth from the Hayworth and the chair conformation back to the Fisher projection. So give me some positions. I don't care what they are. We need 4 chiral centers. This is a good way for you guys to practice when you're doing this for the test. Make some positions up. Okay? What do you want?
Right, left, right.
Okay. Okay, so is this a D or an L aldohexose?
D.
It's a D aldohexose? How do you know?
Oh, the last one.
The position.
The configurational carbon is the last chiral center in the chain. Remember, our numbering system here is from the most oxidized carbon down. So our last chiral center tells us D or L. Right, and that's arbitrary. They could have picked 2, 3, or 4 to do that too, but they're just picking the last one because there's always going to be a last one. Okay? And also, we know in biochemistry that all sugars we have that same configuration, which is nice, right? All the sugars that are used biochemically are all D sugars. So they kind of picked all the ones that we got, called them all Ds, okay? Because they all had that thing in common, okay? So we're going to practice making some different rings here. Let's practice making a pyranose ring. And a furanose ring. So what's the difference between these ones?
Pyranose is a 6-membered ring.
Pyranose is a 6-membered ring. Furanose is 5 furanose, right?
I was thinking the fast and the pyranose.
The fast and the furanose. That's awesome. It's way better than 5 furanose. Or the furanose 5. I don't know. Okay. All right. So we're going to have to figure out what we're going to do to make a 6 and a 5-member ring. Okay, so what do we want to do? What's the first trick we use to figure out how to make these into appropriate ring configurations?
Lay it down.
Tip it down which way?
Timber to the right.
Timber to the right, yep. So I'm going to draw that over here. So it's turning to the right, so we're going to have down, up, up, down. Okay, so I tipped that over. So imagine it's over here the right way, and then it's tipped over onto its right. Okay? And it's important you do that this way, otherwise everything's going to come out backwards. So you have to tip it to the right. Okay? So I want to make a 6-membered ring and a 5-membered ring version of this, and we can either one can exist. So how do we do that? How do we figure out what we're going to use for a 6 or 5?
Now you number it 1 through 6 or 1
Okay.
through 5.
We're going to start at our aldehyde,
Oxidized.
and we're going to number down the ring until we get to what?
Until you get to 5, because you have to end on an oxygen.
Okay, so for a 5-membered ring, we're going to end on, we're going to do a 5,
Yeah.
and we're going to end on an oxygen. We have to end on an oxygen. So we're going to do 1, 2, 3, 4, 5 for our furanose. And then what about for the pyranose?
Then you just go
1, 2, 3, 4, 5, 6. All right, so there's 2 numbering systems. That's going to mean that we're going to close this ring in different ways, right? So we have a ring oxygen for the 5-membered ring here, and we have a ring oxygen for the 6-membered ring here. We're using different oxygens to close the ring. Does that make sense, guys? Okay. So of course we can draw on our blank templates if we wanted to, but let's talk about the mechanism here, right? How are we actually going to close this ring? What are some things we have to do? OHs, are those good nucleophiles when they're neutral and have a hydrogen on them? No, so if we need this to do a nucleophilic attack, we need to pull that hydrogen. Right? So the first thing we're going to do is use a base to pull a hydrogen, or we could pull this one if we wanted, depending on which ring we're trying to close. And then those hydrogen electrons are going to go and attack at the aldehyde. Okay? And once that happens, we're going to break the bond, so we need to protonate. So take a penny, leave a penny, right? In this case, we're taking a proton, grabbing a proton. Right? It's just tautomers. We moved a hydrogen from here to here effectively. Right? Can you see that? Ring tautomer versus open tautomer. Same exact system, just arranged in different ways. Yeah? Okay, so we're going to draw in our blanks, our blank Hayworth projections. A furanose ring is a 5 with an oxygen at the top. Where are our numbers on this? Conventionally, where is carbon 1 on these? To the right of the oxygen. We're going to number through the ring and around. 1, 2, 3, 4, 5, 6. Down here, we're going to have 1, 2, 3, 4, 5. But we're also going to need a 6 because it's a hexanose. Yeah? Yep. What do we do now? So we have our blank templates up there. Now we're ready to start applying those positions from our Fisher projection. First thing you want to do is figure out where that tail goes. That tail is why I boxed these earlier, right? Wherever the position of the attacking oxygen is, that's going to tell you which way the tail goes. If the attacking oxygen is down, tail goes up. If the attacking oxygen is up, tail goes down. Okay? So let's start with our good old Pyranos friend. Tail go up or down? Attacking oxygen is down, so the tail goes up. What about for furanose? Attacking oxygen is up, so where does the tail go? It's going to go down. So we actually need to fix this guy. The tails go down, so that means our 5 and 6 flip downwards. Can you see that? And this all comes from having to rotate into the attack configuration. If you're rotating one direction to attack, that moves the tail the opposite direction. Because these are all tetrahedra. Right? So when you rotate like this, the tail goes up. You rotate like that, the tail goes down. So far, so good?
What about the hydroxyl group?
Yep, that's going to be hanging off. Because that's a prochiral carbon, right? It doesn't matter where that goes. Do you guys remember what difference between chiral and prochiral is? How many chiral centers do we have up here? 1, 2, 3, 4 chiral centers. How many prochiral? We have the prochiral one up here. What makes something prochiral? It's one away from being a chiral center. It has 3 different groups.
Why didn't they say it as prechiral?
Prochiral means pre, right? Like prototype, right? It's the before the actual type, right? So it's just old language from Greek, right? That's what scientists do, is they use Greek words to sound fancy, but they're the same thing, right? So prochiral just means early chiral or before chiral. Okay? So we got these guys. We have the prochiral center, so I just stuck those on. We generate a new chiral center when we do this, right, at the 1 position, because we have either alpha or beta that pops up. But that tail one always stays prochiral. Why is the top one prochiral?
Because of the double bonded oxygen.
Double bonded oxygen means you have 2 bonds to oxygen, effectively. What about the tail? Why is that prochiral? Because what? 2 hydrogens. If you switch to hydrogen for iodine, it would suddenly become a chiral center, right? Does that make sense? Okay. So what do we do next? Yep, we're going to work back towards number 1, around the ring. It doesn't really matter. You have them labeled, so you can do it whatever way you want. But I like to work my way back through the ring. So for our Pyranos, I'm going to go up, up, down. What about for furanose? Up, down. We have those two. 3 and 2 are easy. What about 5? It's not in the ring at all.
Comes off of
Well, we have an OH and an H on that thing, right? But we have to maintain chirality. Is that an R or S stereocenter? Carbon 4. It's on the left, so it's S. So that means we need to apply wedge dash here to make it S, to keep it S. Okay, so what are our priorities on this guy? On this, we have a chiral center here, correct? We have ring, H, OH, and CH2OH. Right? So what's our priority? Read? Hydroxyl's 1. Okay, hydrogen's 4. What's position 2? CH2OH or COC? How do we know? Okay, so this one we're going to tie at carbon, right? Carbons, what are they bound to? Here we have 2 H's and an O. This one is bound to O, an H, and a C. The ring is number 2 priority. You see that? Because in this case we tied everywhere except for C beat H. So our third priority is, or our second priority is the ring, and third priority is here. 1, 2, 3, connect them. Does this look like S to you? Yep, so that means OH stays on the wedge. And H goes back onto the dash. 1, 2, 3. Yeah? That's what's tricky about those. If you make a 5-membered ring here, you have to maintain that chirality. All right, cool. Everything is kosher so far. What do we have to do now with carbon 1? Okay. Are we going to get direction out? Are we going to get something selecting alpha or beta when we do this? When this ring closes, does it have to attack from the bottom or the top? No, it's going to be random. Right? We're going to make an anomeric mix. Right? So we're going to have 2 forms of this. Yep.
Is that last one supposed to be R? Is it that one the
Oh, carbon 5. Carbon 5, yep, you're right. Sorry. Carbon 5 is R. I was looking at 4. Yep, so that means we just need to invert that.
Actually, that was my fault. I think I said L.
No, I should have checked you. So correct that. Right, because this should be carbon 5 is R, and so this one needs to stay R. It looks like S, but is R. It's always good practice to number these. And I won't take points off or anything if you just number them. It's a safety insurance policy. Okay, so we have these two. What about for our furanose? Do we have alpha and beta there too? Yep.
So because it's receiving, we can do that squiggly line, can't we?
You can. That's the easy way to draw it. I'm drawing both just for thoroughness' sake. Which one is which?
Beta, alpha.
What is our, this, Amanda says this is beta? How do you know? OH is same side as the tail, same face as the tail. This one's up, OH is up. This one is then opposite sides. This would be our alpha anomer. All right, now tricky part down here. Which one's alpha, which one's beta? Alpha's on the left. Can you see the OH is on the opposite face of the tail? What about this one? OH
Beta.
is same side, so that's our beta. So it's all about, that's why I tell you same side, opposite side. It's not attack from the bottom or attack from the top. You have to think about it relative to the tail. It's alpha for anti, if that helps you. Right? Cool? Where are you getting stuck there, Rachel?
It's more or less like if I'm given the ring
Okay.
and then I have to draw a vision projection.
All right, so we've done this part.
Yeah.
I'm going to give you now a ring, and let's work backwards. Okay, so we're starting with this strange ring form. You should immediately be able to tell a couple of things about this. And yeah, you should be able to tell. What's a couple things you know immediately about this sugar? What kind of a sugar is it? Okay, this is, Hunter says this is alpha. Okay, what else? Pyranose? What else? How many carbons in this thing? It's a hexose. 1, 2, 3, 4, 5, 6. That'll help us. What kind of a hexose? It's a D or L.
L.
How do you know?
Because of the way the tail is.
Tail's down. Remember when we were talking over here, if the tail is up at that position, that means it's going to go tail down. And if this is a pyranose, when the last one, the configurational carbon, has done the attack, right, the last chiral center, you know that that's going to be an L. So this is an L hexose. Okay, so we know a couple things. We know that, is this an aldose or ketose? Can we tell? Where's carbon 1? Is there another carbon hanging off of that? No, it's a hydrogen here, right? So that must mean it's an aldehyde. A ketose in the same system would look like this. What do you know about this ring? This one's a D. What else is it? How many carbons? 1, 2, 3, 4, 5, 6, 7. So what kind of a sugar is that? What's the name of a 7-carbon sugar? Heptose. Yeah? Anything else? Ketose or aldose? Yep, you can see our hemiacetal carbon has another carbon hanging off of it, so it's a ketose. Yeah?
That's what you look for, is if your hemiacetal has a carbon.
Yep. Yep. In this case, we just had a hydrogen hanging off. That's the old aldehyde hydrogen. This one is the ketone position. There's a carbon hanging off of it.
Non-reducing, right?
Oh, this one still has a hemiacetal, right? So these are both reducing sugars. Right. If this had an OR group here, though, it would be non-reducing. Yeah? Okay. So what are we going to draw for our Fisher projections here? What is our blank Fisher projections going to look like? How many crosses are going to be on them? For aldose.
4 for that one.
4 for that one, because we have an aldehyde at the top and then a prochiral tail. So it's going to look like our classical blank. What's the blank for a ketose look like? What's at the very top and bottom? CH2OH, CH2OH. What's in position 2 for a ketose? Yeah, ketone. We have 3 accounted for carbons. Therefore, we must have 4 chiral centers. Up here, we also have 2 accounted for carbons, so we'll have 4 chiral centers. Right? And you could actually identify those here in the ring. 1, 2, 3, 4. 1, 2, 3, 4.
So why are you doing the aldose and ketose instead of just like the CHO stuff at the top?
Oh, just so you can see it. I mean, you can just write CHO if you want. I'll know that that means this.
Oh, okay. No, that's
but this is just so you can see the structure.
Okay. So you're looking at the OH that is attached to the ring oxygen?
Yep. That's attached to what carbon here? This is attached to carbon 1 and carbon 5. This one's attached to carbon 1 and carbon 6. Right? 1, 2, 3, 4, 5, 6. 7. Right? 6 is set in the configuration. 6 is attached to the tail. Tail's up. So what do you know about carbon 6's configuration? If the tail's up, what side is it on? Right. We knew that because we called them both D, right?
And you know that one's a ketone just because you have a CH2OH on both ends.
You got it.
There's nothing else that could be at that point.
Nope.
I thought the furanose at the top, the aldose is an L.
Oh, it is an L, right? Because it's an L hexose. So that means that this one needs to switch. Yep, good catch. Do you see how that changes it? If you number these, you can kind of keep track. The one that is attached to the tail, if it's tail down, that means that it is on the left side. If it's tail up, it means it's on the right side. Yeah? Okay, what about our other positions? Well, we can number them just to make ourselves happy. Give ourselves an insurance policy against making a silly mistake. And we got them numbered here. 1, 2, 3, 4, 5. Okay, what do we know? Well, we can always, first thing we do when we're making these is tip them on their sides, right? Four, 3, 2. So what's 4? Is it going to be up or down? It's up, and therefore it's syn to on the same side of the Fisher projection as this one. You can think up is left, down is right. So what about 3? Are those both down? And therefore, if we were to tip this back up, right, 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 right. Yeah? What about our ketose friend? Ketoheptose. Okay, remember if it's down here, what is it? Right or left on the Fisher projection? Down is right. So 3 is OH. 4 is right-hand OH. What about 5? Is it up or down? Up. So therefore, left. Does that make sense, guys? Rachel? Satisfied? All right, let's do another one from a chair configuration. Okay. Okay, so we're going to start from a chair configuration. And let me put some decorations on it. Yeah.
So when you're trying to do the chair, you go every other is like up equatorial, down equatorial, right?
Yep.
Because I never know how to stick things up.
Uh-huh. Yeah, it's going to be equatorial, top one equatorial, then axial, then equatorial, then axial, then equatorial. You just practice it. I mean, that's the only way to get good at it, is just to draw a bunch of them. Okay, so this is the equivalent to a Hayworth projection because the oxygen's in the same spot. Yeah? So we want to first go to a Hayworth and then go to a Fisher. Okay, so what can you tell me about this good old sugar? What are some things we can tell immediately from this sugar that are going to help us get to where we need to go?
It's D.
It's D. How do you know?
The tail is up.
The tail is up? It looks like it's equatorial to me.
But it's still up.
It's on the top face, right? Top face. That's one thing we want to keep in mind here. As you can, and on an exam or something, you could take colored markers and mark these in equatorial axial if you wanted to. I've had people do that and be very successful at it. Oh, come on, orange. I guess you get to be green today. So these are bottom face, bottom face, bottom face, bottom face, bottom face. This one is below the equatorial. This one is below the axial. This one is below the equatorial, right?
And we know the ketose.
Okay. It's a ketose. It's a D-ketose. What else? What?
There's 7 carbons.
7 carbons. So it's a D-ketoheptose. Yeah? How do you know it's a ketose? CH2OHs on both sides, right? Okay. So let's draw that in. Is it a pyranose or furanose? Yeah, you can't have chair configurations of a 5-membered ring, right? They have that one kind of envelope flap fold that we see with 5-membered rings. But chair configurations are 6-membered rings. So we know that much about it. So let's draw in our blank Hayworth projection of a pyranose. Okay. What are we going to do? Oh, let me do the color codes. All my bottom faces are going to be green.
So you'd allow us to bring
Yeah. If you want to do crayons, that'd be awesome. Draw me a little picture of a tree and a house on your extra credit page. Okay, what are we going to do? Rachel, you know what we're going to do here?
I would number carbons.
Yeah, you. What are we going to do?
I wasn't here before this.
Okay. So a good first step, like Amanda said, is to number your carbons. That's always a good thing to do. It'll always help you. It can't ever hurt you to number your carbons, as long as you're doing it right. And that can be hard to do because sometimes that CH2OH, people will just get used to writing 1 here at the branch point and skip over that one, and then you draw a 6-membered and your Fisher is all messed up, and it's a mess, right? So be sure you're getting them correct. Going from the CH2OH, this can be 1 or 2, depending on what's hanging off of it.
If it was just an OH, it's 1.
If it's just OHH, it would just be 1. But if it has a CH2OH on it, you know that's going to be carbon 1. Okay, so what do we got here?
We can just go off of our equatorial and axial.
Okay. So equatorial axial, they have them color-coded. Read.
Are we able to go back to the chair confirmation, are we able to figure out if it's alpha or beta just because looking at the 2 CH2OH,
Yeah.
they're both in the top position?
They're both in the top position, which would mean that they're what?
Beta.
Beta, yep. The big groups are on the same side. The tail's on the same side as the CH2OH. Yep, that's a beta D ketoheptose. Now, that's different from when we were talking about aldoses. For aldoses, we would say that this is beta because the OH is the big group on that carbon is the same side as the tail. Here, with the ketose, the big group is now the CH2OH, and that's on the same side as the tail. Right? So I would call this beta, and I would call a very similar structure where OH is down for a ketose also beta. It's about the big group, not about the OH. Big group, big group, big group, big group. Does that make sense? So be careful on those. Yeah? Okay. So what are we going to do now? We got it all decorated. We talked about, now we know it's beta. We know it's beta. Where's our positions going to go? It's got to be the same. The CH2OH has got to be on the same, either bottom or top of the ring. What are we going to do? What?
Top.
And how do you know?
So the CH2O, well, yeah, they're on purple. But
Yeah,
also
exactly.
because we just said that they were on top, so.
Well, they could be both on the bottom also and be beta, right?
Yes.
Yeah. So I have them
just
colored.
on the same side.
Yeah, same side. So I've defined the top face as purple, and I have them on purple lines in both of them. I could have said the bottom ones are top face and put them on green lines, and you still would have been correct. You just have to define that.
But then it would mess with the DRL, wouldn't it?
Well, the ring flips can be a big part of this too, right? We could have also flipped this ring, and it could be in the wrong conformation. So that adds some complexity to these. So we just want to do it straight up from the chair conformation first and see what we get here. Okay? So what are we going to do now? Let's just apply our color code across, right? 5, I'm going to number these. 1, 2, 3, 4, 5, 6, 7. Carbon 5, OH is purple or green? Top face or bottom face? Top face, purple here, right? Axial. Then also purple. Then bottom, green. Then OH is here on the bottom. Does that make sense?
This isn't the most stable.
Is it?
Like, wouldn't you want them all?
How many equatorial groups do we have? 1, 2, 3, 4 equatorial, 2 axial. We want the majority of groups, especially the big groups, the CH2OHs, to be equatorial.
Oh, so it is.
This is the most stable ring form, the most stable chair form for this molecule. It's not the most stable globally for all sugars, but for this one, it's either 2 and 4 or 4 and 2, and 4 and 2 is going to win.
So why wouldn't the CH2OH want to be away from the other big group? Because they're just not big enough that they're...
You mean like right here? Why are they on the? They look like they're crowding each other here, right? Well, because of the chair conformation, they actually in equatorial get farther away,
Okay.
right? If these were both axial, they would have these 1,3 diaxial interactions and smack into each other, right? That's why they favor the ring flip form. You remember that from organic, right? The flagpole interactions, right? The 1,3 diaxials. That's what causes ring flips, right? So as long as the big groups are equatorial, that means that you're going to get the stable configurations. Yeah, Hunter.
Would it be possible for the OH on the 5 carbon to also be an equatorial?
The OH on the 5 carbon?
Yeah, so it would be a 5 equatorial.
Yeah, but that'd be a different kind of sugar if this one was now moved to an equatorial position, right? Remember, that'd be an epimer, where we changed one chiral center of this sugar. Yeah? So changing any one thing about this without changing everything means that we're going to be an epimer. And that means a different sugar.
How many different sugars are there?
Well, let's think.
Because we have glucose and fructose and sucrose.
Let's at least do the Fisher projection here, and then we'll talk about possibles. Okay? Okay. All right, so let's go to the Fisher. What do we know about our Fisher immediately? It's a ketose, and how many carbons are in it? 7. So I'm just drawing in my blank ketose. 7 carbons. We have 3 of them accounted for. That means we have 4 central chiral carbons. Okay, and I'll number those. Blackie. Come on, Blackie. Okay, so remember our trick for when we did this on the last one? If you really want to, you can do it on its side. Or you can remember ups are lefts, downs are rights. Right? So 5 here is going to be left. 4 is left. 3 is right. What about number 6? How do we know number 6? 6 is the one that's been ring contained, right? Its oxygen was used to do the attack. So how do we know that goes on? Tail is up, therefore tail is up, therefore the thing must have been down, and therefore it is on the right. We already called it a D as well, right? Because the tail was going up. Right? And so you remember that this one's D because it's on the right. Okay. So there's our good old ketoheptose. Is this beta or alpha in a straight chain? Is there meaning to beta or alpha in a straight chain? That only happens in the ring form. Right? That's because we get this randomized attack at the ketone position that gives us an up or down. That doesn't exist here. We actually add a chiral center in the ring. Right? We have 1, 2, 3, 4, 5 chiral carbons in the ring, only 4 chiral carbons in the fissure. That attack generates a new chiral center. Okay, so how many possible ketoheptoses are there? Theoretically. How many chiral centers does a ketoheptose have? How many chiral centers does a ketoheptose have? We have 4 chiral centers. How many states can each one have? It can be left or right. So that means that the number is going to be number of sites to the number of states, or number of states to the number of sites. States. We did something like this last term. We figured out how many charged forms there are for a particular peptide, right? We had 5 charged groups, and each one can either be positive neutral or neutral negative. 2 to the 5th would be, whatever, 32? Yeah, 32. So how many do we have here? 16. 16 different sugars that are ketoheptoses. How many different aldohexoses? Aldohexoses have also 16 aldohexoses. What about aldoheptoses? 5 chiral centers, 2 to the 5th is 32 aldoheptoses. So it's kind of like a family tree, right? The more carbons you got, the more relatives you have, right? And so, you're a lot like your cousins in some ways, but in some ways you're different, right? And so you might have all the same sides, and then you have a cousin that's kind of out there, right? And none of us have weird cousins. You have a weird cousin? Oh, you're the weird cousin. That's cool. Take pride in yourself.
So are most of these cousins, are they just mostly when we break them down to try and use them? Or like how many of these then are found in nature? Because I feel like there are just, your like classic 5 that you find in nature, or just a number you find in nature, and then the rest of them you change up somewhere in your metabolism or something.
Yeah.
So I'm just curious.
In our bodies, we use between 3 and 7 carbon, and you almost never see anything bigger, right? But that doesn't mean that you can't, right? And so we'll talk here in a second about how to flip between these, okay? But does everyone get this kind of idea of how to convert back and forth from Fishers to chairs to Hayworths? Feeling good about that? Okay, so that's literally all the thing I can throw at you. So if you can master this stuff that we've been talking about, you're going to be in great shape on the exam. Okay? So what does glucose look like? Let's say alpha glucose. What are our positions? Right, left, right, right. right? At least you should know that much. Therefore, what is it in our Hayworth projection?
Down. We start on the right to the right of the oxygen. That one would be down alpha.
Okay, so you know tail's up here, right?
The tail's going to be
D's
up.
have tail ups, or at least that much. And we know it's alpha, and so it has to be opposite to the tail.
Stay down.
Okay, and then we can say right, left, right from there, or right, left, right, however you want to do that. 2, 3, 4. 2, 3, 4. It's right, it's down. It's left, it's up. There's alpha glucose. Yep. Yeah.
So is beta glucose normally the one, like, that's the most stable, isn't it?
It is the most stable chair form of the aldohexoses, right? Of the D-aldohexoses, but that doesn't mean that it's the most stable of all, right? It's all relative for what you are.
Yeah.
Is it okay?
It likes,
It's at 11% now.
and it stopped charging.
Let's see.
We'll do our best.
Yeah.
It's just gonna die in the middle of me talking. So. All right. So we have glucopyranose. That'll be the full name for this. Glucose in its pyranose form and its alpha. What are some different sugars that we might ingest? Sucrose. Sucrose is a disaccharide of glucose and fructose. So we just bust that thing open with an invertase, right? We can get our glucose out of it. Okay. What else could we get? Can we get any of the cousins of glucose?
Yeah, galactose.
Galactose, do you know what its positions are? Look it up quick, read.
Isn't galactose just an enantiomer? Or no, it's a diastereomer.
Yep, so will you show me?
Yeah, I can.
Look it up really quick.
Faster, Reed. Come on. You're slacking.
Wasn't right up?
Right is down, left's up.
Okay.
So what's galactose?
So it's going to be right, down. Or left.
Left.
Right, left. That's what I thought it was.
Fisher is left, right.
I'm just going to look up a Fisher projection now.
You're making this so difficult.
Galactose. Left. Nope. It's right, left, right.
Yes, there we go. It's like pulling teeth.
I was looking at L-galactose.
Yes, that's not the one you want. Okay, what's the relationship between these two? Glucose and galactose. Yeah, they're epimers of each other. At what carbon?
Carbon 4.
They're carbon 4 epimers. Okay, where might you find galactose? Where might we ingest galactose?
Lactose
Milk.
isn't a disaccharide.
No, galactose is a single. Lactose is a disaccharide.
Oh, lactose is galactose.
Yep. Lactose is galactose and glucose, right? So if you're drinking milk, eating lactose, right, are you going to throw away half the sugars that you just got? No. So we need a way of switching those between each other, okay? So we need some sort of an enzyme to help us with this so we can make energy out of it, right? Okay. What do we got? What's the positions on the Hayworth projection here?
Or no, so it's going down.
This is tail up, down. Left side up, right side down.
Gotcha.
So what is the difference here? Carbon 4 is either up or down. Right? So how can we convert between these? Is there a way to convert between the two? What are we going to have to do to switch those positions? Nature isn't just going to do this and draw it on the bottom. Right? We have to find a way of moving it from one side to the other.
Beta rotation.
Yeah, we have to do something like beta rotation, or we move it back and forth. But in this case, we can't do that because we can't kick off the leaving group. 4 doesn't have anybody to kick him off next door,
Check it out.
right? And so we have to use an enzyme that switches between apomers. Can you imagine what this enzyme might be called?
Epimerase.
An epimerase, yeah. An epimerase. Okay. Can you imagine why that might be called that? Okay.
No.
Epimerases use NAD. But only as a cofactor. You regenerate it. It's not net making any energy out of it. We're just using it as a cofactor. So really what we can imagine is it makes NADH, and then it switches it right back to NAD. Okay? What is NADH used for?
Two electron transfer.
2 electron transfers and reductions. NAD is used to do reductions. That means we have to oxidize our good old galactose molecule here, right? What is an oxidation? Losing oxygens and hydrogens, right? Which hydrogen are we going to lose here?
Probably the one on 4.
4.
Carbon 4.
Yep. So can you show me a mechanism for how an epimerase might work? It has NAD, so let's draw NAD first. How might this work? Epimerases have NAD built into them, or carrying it around as a cofactor. How might this work?
We need the OH to leave so it can come on the other side. So we use it to, if the OH gets broken.
That's one way to do it. That's like for doing like butarotation, we have OH would travel. Does NAD move OHs?
No, but I'm saying if we do eventually move one, because we can kick off an H on there, as it is right now.
Okay.
If we kick off the H, can then the H attack the carbon and kick off like water?
Yep, we're doing this backwards, but we're not kicking off a water here. We're going to be moving the hydrogen from one side to the other. Okay? So we're going to need a base. Just like we always do for NAD oxidations, we need to get that hydrogen off the oxygen because we need to push that hydrogen off. Okay? So we grab the hydrogen, make the double bond, transfer it onto NAD to make NADH. We have an intermediate here. We have an ADH. What happens now? We have a ketone inside the ring. What do we need to do to get back to glucose?
Need to push through.
We need to put the hydrogen back from the top, right? So we're going to push back to our ring. And then we're going to grab that hydrogen back that we just took off. And that's going to help us convert to this would be alpha D glucopyranose. So we can switch between epimers. Epimerases can do that. You have carbon 3 epimers, carbon 4 epimerases, all sorts of different ones to convert them to a usable form. That way we don't need to have whole pathways just for galactose. You just make it into a glucose and use the same one you already got.
Are they just moving that ring then after it gets protonated? Because they would need to place it. So
the NAD is actually kind of planar with the ring, and it just depends on, kind of roughly is it tilted this way or tilted this way, right?
And that flips upon protonation. So that way, like, if you're
Yep.
above the ring, you could grab the H from above, and then
Yep.
you flip below, so you make sure you attack from below.
You got it. Yep. And this is reversible, right? We could always just decide, hey, I don't really like glucose anymore. I want to be galactose all the time, right? Now, since our flux is taking glucose away and it's going into glycolysis and things, then we're not going to be switching back to galactose, right? It's going to be, as soon as we make a glucose, then we're going to use it up through glycolysis. So most of the time we never reverse because the flux is pulling it in this direction. Yeah?
I was just going to ask, like, theoretically, like, we could go back, but would we ever, because even if we get to glucose, but we don't, the demand isn't high for glucose, we just go to glycogen at that point, right?
Yeah, our bodies do, but like cows need to make lactose, right? Lactating women need to make breast milk, right? All of those things are making lactose, right? So this happens in your bodies, right? It just needs a special type of cell that has these enzymes in it and allows the backwards transfers.
Okay.
Yeah? Does that make sense? So that's epimerases. In this case, NAD isn't used or made net, right? It just is a temporary holder for hydrogen. So you can switch it from side to side, right? So this is like the backwards version of meter rotation. The OH moved in the other one. Here the hydrogen's moving. And so we need a special hydrogen carrier to do that. Yeah? Questions on that? Cool.